In this video, we begin a discussion of the second class of reactions in solution that we're going to study, and those are going to be acid-base reactions. In order to understand acid-base reactions, we need to have an operational understanding of what an acid and a base is. The definition of acid or base that we're going to be using most commonly in this part of the material is going to be the Arrhenius definition, which says that an acid is a substance that provides protons in solution, and then a base is a substance that provides hydroxide ions in solution. All right, so let's see how an acid is able to provide protons in solution. Let's take hydrochloric acid. HCl, we put it in solution, and what happens is that when you put hydrochloric acid in water, okay, it dissociates to generate protons and chloride ions. So clearly, hydrogen chloride is an acid according to the Arrhenius definition because it's able to provide protons in solution. There are other types of examples. For example, we can take acetic acid, which has this chemical equation. Okay, aqueous, put it in solution, and that generates also protons, aqueous, and acetate ions. CH3, COO minus, AQ. We commonly write this acetic acid simply as HAOC, and this acetate ion simply as AOC. Okay? What about bases then? Well, bases are, according to the Arrhenius definition, are substances that when put in solution are able to generate hydroxide ions. Okay, so sodium hydroxide, for example, is a base. Okay, because when put in solution, you generate sodium ions. Okay, and hydroxide ions. Okay, there are other types of bases. For example, ammonia is a base. Okay, because when you put it in solution, okay, in this case, you need a water molecule for the stoichiometry to work. Okay, L generates ammonium ions, NH4 plus, aqueous, and hydroxide. Okay, and again, this is the Arrhenius definition of acids and bases. As we will move through the material, we will see that there's a more advanced definition of what an acid and a base is, which is the Bronsted definition. We don't need to work with that just now, but just for the sake of completeness, in the Bronsted sense, an acid is a substance that is a proton donor. Okay, so you can clearly see how these substances are proton donors. And then a base will be a substance that is a proton acceptor. Okay, so it's not obvious why these substances are proton acceptors, but suffice it to say that this hydroxide can accept a proton to generate water. Okay, so again, we will see that later. Now, something that you may have noticed is that in the top chemical reaction here that we have the dissociation of the acid and the base, I will have a forward arrow, but in the bottom ones, you actually have reversible arrows. Okay. This is to separate the two types of acids and bases that we can have. When you have a strong acid, it turns out that the dissociation is complete. Okay, so hydrochloric acid is a strong acid, which means that there's nothing or a negligible amount of HCl left in solution with a dissociation, and all of it, or most of it, is going to be protons and chloride. Okay, but there's also weak acids, and weak acids are those that are not fully dissociated. For example, acetic acid is a weak acid. And what that means is that there's going to be a lot of these molecular species in solution with a dissociation, but there's going to be also a few protons and a few acetate ions. Same thing happens with bases. Okay, sodium hydroxide is a strong base. The single forward arrow means that this base fully dissociates in solution. In the case of ammonia, you have the double reversible arrow, which means that there's going to be some ammonia that actually is not forming hydroxide and ammonium ions. Okay, instead it remains as ammonia in solution. All right, so we need to know a few of the strong acids that we have so that we can do problems with them. Okay, so there are strong acids for these course are going to be hydrochloric acid, hydrobromic acid, hydroiodic acid. Then we're also going to have nitric acid. We're going to have sulfuric acid, and then two more, chloric acid and perchloric acid. Okay, that's the list of strong acids that we have to know for this course. Now, what about bases? The list of strong bases is going to be a little shorter. Strong bases. Okay, we're simply going to consider that a strong basis will be sodium hydroxide, potassium hydroxide, and also calcium hydroxide. Okay? All right, so in the next video, we're actually going to start studying acid-base reactions. Okay, and we can actually get it started here a little bit, just to show that an acid-base reaction is often called a neutralization reaction. Okay, so for example, let's make a strong acid, hydrochloric acid, react with a strong base, sodium hydroxide. Okay, this is going to generate water and sodium chloride, which is soluble. Okay, so why is this a neutralization reaction? Well, you take something that is an acid with something that is a base, and you get to a neutral point, okay, where you don't have either an acid or a base. Okay, so you get water and then a salt. All right, so the typical acid-base reaction is going to be acid plus base to generate water plus salt. Okay, in this case, the salt is soluble, because you'll have sodium ions and chloride ions free in solution. Okay, and water is generated. All right, so in the next video, we're actually going to learn how to do acid-base titrations, which is a way to analyze how much acid or how much base you have in solution.